Il a fait sa thèse là-bas, une thèse sur la turbulence et l'effet dynamo. Après ça, il est parti sur un poste, un financement Marie Curie, un financement européen, à Oxford, au département de maths. Il travaillait avec Alain Gorielli sur les problèmes de stabilité de structure élancée. Et puis il est maintenant à l'EPFL, à Lausanne, en Suisse, où il est lectureur dans le département de maths. Et il travaille sur des problèmes de modélisation de croissance de filaments biologiques, donc vus aussi comme des structures élancées. Je pense que c'est ce dont il va nous parler aujourd'hui. Voilà, merci.
Merci Sébastien. Hello everyone. I've been asked from somebody in the room if I could give the seminar in English, which actually works for me because I had prepared it all in English. So I'm just going to do that. Right. So I know that you've heard about filaments because you have Sébastien in the group, and then you have Arnaud in the group, and I'm sure others have done as well. I just want to say a quick word about modeling with filaments versus modeling with 3D mechanics. So we're going to talk about these today, and I expect that that tells you absolutely nothing for now. And the aim is that by the end of the presentation, these three pictures should be very familiar, and you should know what I mean. My aim of doing all of the theoretical work is to be able to model these sort of things. And of course, just doing filaments, you won't be able to do all of that. But the idea typically is to, at some point, you do three-dimensional mechanics, then you get effective properties, you feed that to a filament Kirchhoff sort of model. We'll talk about that. And then you can stability in your theory. So that's the way I'm looking at it. We've worked on the tongue of the chameleon. We've worked on a plant called cardamine. We're going to talk about those two shortly. And then things that we have in mind that we'd like to do is big growth in plants, whatever is long and thin in the animal kingdom. I would really like to get to the spine. We can talk about that after the seminar. This is very much so a long-term project, but I think I start to have all of the key ingredients to be able to say something useful about that. So let's talk about applications first. Let's look at the chameleon. And that's where I hope I have some sound. Or not. So about the same time we wrote the paper on the chameleon, National Geographic made this video about the chameleon tongue, and that pretty much sums up. Oh yeah, the sound is coming up. That pretty much sums up the paper. The idea is that the tongue goes really fast, and the way this is achieved is by building up slowly elastic energy within the tongue, and then you have an you change the stability of your system. We're going to talk about that. So this is real time, and this is really, really fast. There. And so the idea is that you build up the elastic energy very slowly, and then you go through an instability, and you release this elastic energy, and you're able to achieve very fast motion. So why is this good for the chameleon? Well, one of the really cool parts. Why? Okay. One of the really cool parts is that the motion of the tongue, the time scale it takes for the tongue to shoot, is actually shorter than the time scale it would take for muscle contraction. So once the tongue leaves the mouth, that insect does not stand a chance because it does not have physical time to contract any muscles. So if the chameleon aims well, it always hits. And the way this works, we build all of what I'm going to talk about, almost all, has been done in collaboration with various people, and I'm going to cite them as we go along. So this was part of my work in Oxford. My two partner in crimes for a long time have been Derek Moulton and Alain Gorielli, and Stefan O'Keefe was a student on the project. So with here, the idea is that inside the tongue, inside the mouth, you may have seen it. The chameleon has a long bone, which is called the ontoglottal process, which we're going to call the bone for short. And around that bone, inside the mouth, there is a sheath that's folded telescopically, and so we draw it as stacked like that. And then around that, you have an accelerator muscle that's very big. So this is, in the movie, you see here that you have the accelerator muscle. This is the very thick part. And then when it shoots, you have this very thin part, which is the sheath, which is folded telescopically inside. Now, we build different models for this, but the short story is that you need to do a 3D model of the accelerator muscles, which is fibrous, with fibers that wind spirally radially. So they dive in. And then, if you try to make a model with only elastic energy in that muscle, you are too low on the speed of the tongue that you can predict. Okay? And the solution is that you absolutely have to add acrylic sheath where the fibers, instead of diving in radially, they are wrapped around in the hoop direction. Helically as well, but in the hoop direction. And so you build 3D models for the elastic energy in those two cylinders. And as you do that, you can build, when the fibers contract, you get to a loaded position where you have an elastic energy and you can predict how much that is. And then what happens is that when this gets a little bit longer than what's drawn here, that you go over the tip of the bone, and then you're able to release that elastic energy because the tongue can just relax and have nothing that they are contracting on anymore, and that you can get an effective force applied from the bone onto the materials that would be on the right here, and that's how you start shooting. And so we did that whole elastic energy balance. This is velocities from the chameleon tongue from experiments, and this is our base models. And we played with different fibers, orientations, and so on and so forth. But essentially, our predictions is that we get 6.1 meter per second at the end of the day. So we counted that as a success story. But the whole take-home message here is that you build a 3D model to figure out how much energy there is in your system. Then from that, you infer effective elastic properties for a filament, the tongue, and then you just solve for a filament in 1D to predict the mechanics. Okay? And of course, you could also do your 3D model for all of the material and try to integrate over time and do the full equations in 3D, but this would be very expensive and it would take a lot of time numerically, and you wouldn't get any more insight. So here is what we're going to talk about. We're doing a few examples. We're going to talk about the chameleon and about Cardamine. I will take a little bit of time to remind you about Kirchhoff theories for rods. And then there are 3 theoretical projects I'd like to mention, and I hope I'll have time to go through all of them. So the other thing we modeled recently is this plant called Cardamine hirsuta. For scales, this is a dead oak leaf. And essentially it's a weed. You may have it in your garden, it's very common. You would probably want to discard it as being ugly. But if you come close to it, it's going to sound like popcorn. It's going to send its seeds flying all over the place. And that was the thing that was interesting to the biologists that came to see us about it. And we tried to build a model of that. So here is a movie of what's happening. It's slowed down heavily. You can see some time frames down here. The seed pod is about 2 centimeters long. And those seeds are going to fly about 1 meter away from the mother plant. This was done in collaboration with so Hugo, Annelies, and Angela are all in the Max Planck Institute for Plant Breeding. So they were absolutely fantastic experimentalists. They did wonderful experiments to figure out all of the constant we needed for the different models. And then we made mechanical models with Derek again and Alain. And Richard Smith numerical I'm going to talk about in a second. So the idea is to predict this motion and you predict the density of seeds around the plant, essentially. So, because this habit of seeds is probably they know the whole gene. Everything there is to know about that plant, I feel like to say. And so, because it's very close to something they know very well, experimental techniques that apply to Arabidopsis apply to Cardamine, but the cool fact is that Cardamine catapults its seeds while Arabidopsis doesn't. Okay, and we'd like to understand what is the difference between those close relatives that allows for that to happen. And we'll see that there are 2 innovations that are required. So this is plant Cardamine. This is a seed pod that's about 2 centimeters long. Let's zoom on that. It's flattish. So and the width of this flattish ribbon is about 1 millimeter. If I take a section and I look at it, now I'm looking across this. You see that there is a medium part that's called the rhiplum. This potato here is a seed. That's the point, it's the thing that's about to fly. And then you have 2 valves on either side, which are here and there. And these are those that are going to coil. So if oriented like this valve is about to coil this way, shooting seeds that way, and towards you as well a little bit. Okay? And what we need to understand is the mechanic of those valves. So we're going to zoom onto the cell layers. I zoom on it and I rotate it. So this is inside of the seed pod, this is outside. And we need to look at the detailed structure of that. So on the next slide, I'm going to zoom in. So here we are. So it's the same picture, just seeing it closer. And different things can be noted. There is the layer that's the innermost layer is lignified. So this purple tint tells us that there are lignin there. And that means that, so lengthwise is this way, widthwise for the pod is that way, and then height, for what I'm going to call height, is up in this picture. Right. So the idea is that because it's lignified, this bottom layer is completely inextensible lengthwise. But the thing that's special to this plant species is that you have those U shapes of the lignin, and actually they are weak at the bound. So if you look at the lignin, you have a shape that looks like this, and then this goes 6, and then this goes very thin here, then again, then very thin here, and like that. And the point of the thin parts here is that this is able to open up, okay? And so width-wise, this is not extensible at all. This layer can expand width-wise, and we're going to see that this is crucial. That's one of the innovations. For comparison, in Arabidopsis, the other plant that's well-known and that does not eject the seeds, you have boxed lignins, so this cannot expand width-wise at all. Now, because just before that, we had a paper about the opening of seed pods in lilies. And what happens in lilies is that you have an outer layer that desiccates, it dries up. If the outer layer dries up, it shrinks, and so as it shrinks, it makes the whole thing happen, open. Okay? And so as a result, we had made a model with an outer layer that's active in the sense that it dries up and so shrinks, and because it shrinks, it opens slowly and things are easy. So now we thought, okay, it must shrink somehow much faster. But how? And then we started to think along those lines, and then our experimentalist friend come back to us and say, oh yeah, that's good, you have this model, we'll just apply it. By the way, our valves curl up when turgor pressure increase. And we were like, okay, that's not possible. You're telling us that when you puff up the external layer, it opens. So this was one of the big puzzles for us. And at first we told them that's not possible, this cannot be. And so they started making more and more experiments on what's happening on this active layer, which for us is exactly the top layer and only that one of cells. Yeah, the passive layer, of course, this is a medium of cells, and you could do a lot of complicated stuff. In our models, we're going to say this is just a homogeneous layer. Its only role is to give a lever to the active layer with respect to the inextensible one, right? So I'm going to model all of this passively. This is going to be active. It's going to try to contract lengthwise, and this is passive but inextensible. So it gives us the rigidity we need to transfer this contraction into bending. Okay, so let's figure out what's happening with those active layers. So they made some imaging techniques, which I know nothing about, where before explosion and after explosion. And that's just those cells, it's actual cells that you see, and you see that the layer indeed shrinks, and it puffs up. So we wanted to understand that, and we wanted to make sure that this was right, that this was not, okay, so now it exploded, so maybe it's different from the stage it was in just before explosion. So some things they did was, you take this one, which is post-explosion, which would look like this, and then you put it in a solution with 1 molar of salt. And what the salt does is that it reduces the pressure inside the cell because of osmosis, right? It's going to drive the water out of the cell. And they see that it puffs back to flattish sort of thing, like pre-explosive shape. So we do believe that this is indeed an active layer. When you increase the pressure, it shrinks. And we wanted to understand that. So this is a numerical model that Richard Smith did. Our first guess was, this is purely geometry. In Arabidopsis, the same cells are long and thin. They're about 100 micron for 20 micron in the other two directions. So this would be the shape of the cell before you increase the pressure. And if you increase the pressure, then it will elongate. Okay? And then we thought, okay, so maybe it's a bit like a cushion. If instead of being thin and long, they are squarish like this, so that's about 50 micron, which is relevant. It's about 50 thickness. If you start with really flat and you pump it, it's going to increase height-wise, but it has to shrink by inextensibility along the length. So we thought that might be happening. And the point is that if now you increase the pressure on this cell layer, what happens is that it does not extend, but you don't see it shrink much. This is really not nearly as much as we would need to explain the sort of number of coils we were seeing on the plant. The only way we could get to that sort of shape under turgor pressure is if the walls are anisotropic. So you need fibers lengthwise to increase the pressure. That was the only way we could build the model that was explaining this. So we were saying, so the numerics was saying we need to have fibers. So the experimentalists went back and checked, and they did see that before maturation, you have collagen tracks which are organized widthwise, and just before explosion, those collagen tracks are redeposited, and the fibers are being deposited lengthwise. And that's exactly what we need to have the anisotropic wall, so that the layer would shrink when you increase turgor pressure. So that matched very well. And once we had that, something else that's important, you can see a puff-up cell here, is that you shrink lengthwise, but the total volume increases. It does increase, you are increasing the pressure, of course it must. And so you are increasing in height, and you're also increasing in width. And that's very important that you're able to do those two things, so that you can shrink by a total amount that your anisotropic wall allows you to do. So coming back to a simplified model, we have 3 layers. That's when the valve is attached to the fruit. W2 is passive. W3 would like to shrink lengthwise, but to do so it must expand in height. That's easy, there is nothing on top of it. But it must also expand in width. And that's where the hinges in the inner layer becomes very important, because it has to be able to expand in width if you are to completely profit from the elastic energy stored in the top layer. And that's why you absolutely need that. So the experimentalists were wanting to be able to check that experimentally, so they made mutant of Arabidopsis which would have the top layer that have the same properties, but with bottom layers which are boxed, and those do not explode. So if you do not allow for the release of energy widthwise, you cannot explode. So bringing all of that together and some of the theory I'm going to talk about in a second, we can write an energy for the layer, and then we look at the energy landscape. And for Arabidopsis, the wild type, we get about 3.5 coil as a minimum of energy, which sorts of match. And if we assume boxed lignin, that's our energy landscape, and that's the sort of bending enough to explode. Now what we did next was, okay, now we have an effective rod model for the valves, and so we can integrate it on the computer, and that's the sort of movie we get. It sort of look good, but we want it to be more accurate. So this is the sort of movie we have if we look at the shape of the valve at different time slots, and then we can follow, for example, the endpoint in blue, and we can see the trajectory that point takes. Or we could take the middle point and follow that material point during the motion. We did that because we can also, that's experimental data. We can also measure what's happening along the valve with a high-speed camera. And this is the data to model match, right? And you have to understand that in this model, we start by modeling fibers in the cell walls. Then we get effective properties for each part of our model. And each time we want an effective property, we have to make a different kind of experiments to measure them. And eventually, we have that sort of match. And then we went on to also make a viscoelastic model for detachment of the seed from the valve, and they get the full distribution of seeds. But I would like to talk about other things. Something else that's relevant, I believe, is that the sort of techniques you can develop for filaments can be applied to biology. That's what I like to do. But it can also be applied to a host of technological applications. We're going to meet those two today. That's another one I have my eyes on. It's a simple fishing line. You over-twist it. You may have heard of this. You over-twist it, and then so it makes a helix. It looks like that. And then when you heat it up, it can contract by about 40%. So that's very, very efficient artificial muscles. And I think I'm close to building a theory to explain these things. All right. So to be comfortable to understand this, I need an introduction to Kirchhoff rods. So what's a filament? Well, a filament is just any 3D material that's longer than it is wide. Okay, so there's one dimension that's long, and the other two which are small, and I essentially assume nothing else. Kirchhoff, in the middle of the 19th century, built a theory for that sort of things, and his first approximation was to say, okay, let's say it's really a set of sections, and because they are small, you can make a dimensional argument to say that the sections don't deform much. So you really have a sequence of sections, and you infinitely many of them, and you want to know how they behave, right? So mathematically, we encode each of those sections by giving a right-handed orthonormal frame to it, which we call the material frame, and which we call D1, D2, D3. And then you have a center line that's called R of S. In general, it doesn't need to go through the center, but it doesn't really matter. And we say that the derivative of R has some components in the local material frame. And the derivative of D, so this material frame, as you walk along the rod, is rotating, and so you encode it by an angular velocity U. But it's velocity as you move along, so it's in space and not in time. But that's the same idea as an angular velocity, like you know. So if you know V and U, then you know the shape of the rod, up to global translation and rotations, but usually you don't care. So once I know V and U, I consider the problem is solved. To solve those D, once again, if I do want to find the shape, but there is no in it, it's geometry. Okay? Right, so now we have the geometry sorted. We also need to do mechanics. So to do mechanics, imagine I have a rod here, and we want to write a balance of force and moments. Of course, I could add dynamical terms, which I didn't, but it's because we're going to talk about statics, but you can totally do it, and we did it for the for the projects I showed you before. So what is N and M? Well, if you make a section of this object here, N is the force applied by all the material on the right on all the material on the left. Okay? And M is the moment applied by all the material on the right on all of the material on the left. And F is a line density of external force, L is a line density of external couple, and then if you do balance of force and moments, you get to those equations, which are called the Kirchhoff equations. Now, the next thing you need to do is constitutive laws, because this is not a closed problem. And so what Kirchhoff did back in his days is to make a small argument. He was assuming inextensibility and unshearability, and that's to say that the derivative of the center line is along one of the material frame, which is a simplifying assumption. It is a very good assumption if you model anything macroscopic. So the unshearability is saying that the center line stays perpendicular to all of the section, and it's very good in a macroscopic object because if I try to shear, what happens is that you get a double bend instead of getting a shear. This is a terrible assumption to make if you try to do you try to do proteins or filaments which are made of atoms and you zoom in to that extent. Then you need to include shear. But for everything macroscopic, unshearability is very good. In extensibility, it all depends on how much force you apply. For a guy weak like me, if I pull on this, I can say it's about inextensible. That's not going to change much. Somebody much stronger than me could pull on it and extend it, and then that would be a bad assumption to make. And it all depends on the sort of things you want to do. But that's what Kirchhoff looked at first. And then you need a law for the local moment. And he said, well, it's proportional to the strain. So here, U is the rate of rotation of the local frame as I move along the rod. And U hat is the rate of rotation of the local frame as I move along the rod if I put it in a space where there is no stress on it. So if I put it in space, do nothing to it, it's going to take a shape. Clearly, this thing would not like to be straight in its reference shape. It's going to take a shape, and that's encoded by U hat. So U minus U hat is a strain, and you get to the moment by, if you put yourself in the principal directions, you get to the moment by using this matrix K, where you have the Young modulus that appears and moments of inertia. So this was Kirchhoff's theory. Now there's a slightly more general way of doing that was introduced by the Kossera brothers beginning of the 20th century, where they say, okay, so what we really have is that density of electrons inside the rod, the rate of rotation and the extension, and potentially on R and D if there are external forces. Now, if you do that, you have a constitutive law because an M in the local frame comes as simply as derivatives of W, and if you do the first variation, you get back to a force and moment balance. And then after that, the story goes on. There is Cohen in the 60s that start to look at, okay, but here we said the material framing has to stay right-handed orthonormal. What happens if the directors are allowed to rotate with respect to one another, right? So you can write more general energies where you don't really have a right-handed orthonormal frame. So you have more and more general theories of filaments that come that way. We're going to meet one in a little bit. Now, what is this for the Kirchhoff case? Well, it's simply a quadratic form in the strains. So that when I take a derivative of this by U, I get back to my linear law for the moment. So keep this in mind. You have a half, and this quadratic form, strain, dot K, strain. We're going to meet something similar, but slightly different in a little bit. Okay, I have everything I need to start doing the cool stuff. So a project we've been working on for a long while now with Alain Gorieli and Derek Moulton is incorporating growth into this Kirchhoff theory of rods. And we did it in stages. The first thing we looked at is what's called passive growth. You say that the material properties, which is essentially encoded in the matrix K of bending stiffnesses, and the reference shape are given by the biology and they evolve slowly over time. And now at any of those times, you can resolve for the mechanics and the two problems are completely decoupled. So you can already do interesting stuff, but you're fairly limited. Now, more interesting things is what we call adaptative growth, where now, and that's what will happen here, you have a plant that has a given shape, let's say now, and because of the weight of gravity, it takes a certain shape. Now let's say that plant is trying to grow, and let's say it adds a layer. That's not how plants grow, but bear with me. Let's say it adds a layer on the outside, for example. Now this new layer was added along the current shape. The mechanical effective properties of this new system on the shape you had in the past. And so you get effects that you can compute k and u hat that depends on the history of the system. So we did this in the first paper, and then another effect that we're going to talk about today in a bit more detail is what happens when you have two filaments, or more than two, but when you have two filaments which try to grow at different velocities inside one bigger filament. And then you can generate effective stiffnesses and effective U hat. And we're going to see that my take-home message in this case is that it's not a Kirchhoff rod anymore. It's a more general kind of rod, more like Cohen. And then something else we work on, but it's very now what the atomic weapon in this sort of objective is to have a theory that would go from full 3D tensor on it. Some people have looked at it from gamma convergence. It's not easy to read, and it's ready to be applied to practical problems yet. There is something that can be translated into something applied to biology. All right, so let's take two rods that want to grow. I have the red one and the blue one. They are attached along the length in a way that's prescribed. And then the idea is that they would like to grow by a different rate. And potentially they would like also to develop reference curvature, which might not agree with one another. So here I drew twist as reference curvature. So what you're going to do is that you're never going to detach them, but in your mind you may do so. You let them grow independently, and then you solve the mechanical problem of reattaching according to the same mapping that you had at the beginning, and then you have a mechanics problem to solve, and you get to that sort of shape. So if you do that, you have 4 strains in each, because we assume they can be extensible. They're each unshearable, but they may be extensible. You have 4 strains for each rod, but there are constraints because you want them to be attached. And so essentially you get to 4 strains for the whole theory. And the model reduces, and I'm going very fast here, I don't expect that's enough to understand the details, but the result is that to the minus and the code that goes from the center line of 1 to four numbers. Then U and energy plus an energy. The total system and theta, but in my life a lot. Okay, so some examples. Let's take the next step. So I fix 2 of my variables. The energy that is essentially that shape. Now V is a function. It's going to have that sort of shape where A is a function of the little d and G is the ratio of the arc length of the 2 rods. So that's the constant that tells me by how much more does one rod want to grow with respect to the first. Okay, so if G is bigger than 1, the plus rod grows more than the minus rod. Okay, so now I have this energy I want to solve for. I do the first variation. The first variation gives me a Lagrange equation with 3 boundary conditions. Okay, and here this is something, is an equation that you can solve easily. That this is derivative by S, but that equation is the same thing as a point mass moving in the potential V. Okay, so this is something you have a lot of intuition for. So let's look at V. When G equals 1, you can find that V has this bell shape. And so let's take U0 hat equals 0 for now. So you have to find a solution for a point mass moving in the potential V. But the thing that's strange is that you, instead of having initial values for theta and theta prime, you have boundary values. You have to start and end with the same velocity. So in this potential, if you want to start and end with the same velocities, the only thing you can do is stay on the maximum. Because if you start here, you're going to keep accelerating. And if you start there, you're going to keep decelerating. You're never going to get back to zero velocity. So your solution is there, and that's completely boring. The two rods have the same length, they have the same they are both straight. Nothing happens, it's just straight. Now, if I start to decrease G, well, the shape of V changes a bit, but it's still a bell, so the solution is still here. And because of this recomputing the shape step, I do get that it bends. I also get effective effective bending properties for this structure, and that's how we could do the whole Cardamine story. So with this, you can already do not only Cardamine, but also other things. So this is an experiment where they have elastic sheets. They grow myocard cells from rats, so that's muscle cells from the heart of a rat. On top of it, the elastic sheet is considered to be inextensible, but it bends. And the rat cells, when you put it in solution and you apply difference of potential, they try to contract. Okay, so this is the movie, and they made many things more complicated than this simple rod, but that was one of them. And so this is very much back of the envelopes of computation. I'm not meaning this as a serious model. It's just an example of the sort of thing you can do. You apply the formalism that's in the previous paper, and you get to a differential equation for the relative growth between the two. And it's an equation with only one variable. So now if I apply a difference of potential that's stepwise like they did in the experiment, I'll solve my differential equation that's nonlinear. I get this sort of shape. I get a radius of curvature, and that's how I make this movie, right? Now this cannot be, this looks a lot like that, but this cannot be right because I did not try to do the fluid structure interaction whatsoever, right? This was just a proof of concept. Okay, so this was for the 2D case. Now more interesting is when I keep decreasing the length of one with respect to the other, the shape of V changes. It goes from this bell shape to an M shape. Now it's very shallow. I still have an equilibrium that starts at 0 theta and stays there, so this is just more bent. But then I start to have another equilibrium, which is we start at the new maximum here, and that's a helical shape. And I could start at stay at another maximum there. It would be the same helix, but opposite handedness. Okay, but now what I was solving was this equation in a V that's M-shaped. Now I kept decreasing G a little bit further. We still have our two familiar solutions, but they start to look different. And now there is another solution, which is a perversion. You start close to a state which is right-handed, and then you swing down that potential, and that potential in the analogy of a point mass moving in the potential, and you end up close to a left-handed helix. And so this is that sort of shape. Okay? So that's cool. We see multiple equilibrium, and then we see more equilibria, and then we see more equilibria, and then we see more equilibria. So we have plenty of equilibria. So the next, and they are all very nonlinear. And if the potentials were a bit easier, you could maybe solve with elliptic functions, but here it's hard enough that even that is not working. And so the question that comes naturally is what of this whole mess is stable and what is unstable? And that brings me to my next point. So there are numerical methods to do that. They are not easy, and in my experience, extremely sensitive to numerical errors, to the point where when I apply do something more theoretical. And we got to the following result. So take a functional that has this shape, and I strong functional must have this particular. Fairly it's pretty much anything. I just that the first and second derivative of V do not vanish simultaneously. But that most V's don't have that, so it's fine. Now I'm not fixing the boundaries, so when I do my first variation, I get Euler-Lagrange, and I also get free boundary conditions. And now I need to prove at second order that the second variation is positive definite. Now for those who have tried, doing that when of your Lagrange equation, which are like theta equal constant, that's very easy. But when the solution becomes complicated, like the sort of solution I showed you before, this is a really hard thing to do. So showing instability, you just have to find a perturbation that shows that this is negative. That's doable. Tricky, but doable. Showing that for all perturbation tau, this thing is positive is a hard problem. What we can do is we look at our first variation. We know we're going to get an equation like that, and so we know it's motion in the potential. So that solution might look like that, say. And we can also, to that Euler-Lagrange equation, we can associate a phase space, and that trajectory draws a curve in the phase space, and here it is. And you see I've drawn vertical lines as well. Blue lines corresponds to maxima of V, and red line corresponds to a minimum of V. So what we did, and it is a theorem, we are completely, there is like no doubt about this, there is no approximation, it's strict. You take that functional, and you find a solution of the Euler-Lagrange equation that draws a curve in the phase space. And you see that if I have an initial velocity, I can go over that bump, and but I don't need to know the exact shape of it, right? I can tell you it has this sort of, it looks like that. I'm not telling you exactly how high it's going to start, I'm just saying this is the sort of shape I get, okay? If I get that, I can build the following index, which is the number of time I cross the maxima of V minus the number of time I cross a minimum of V. Okay, I make that count. Now, if J is strictly positive, I know the equilibrium is stable, and if J is strictly negative, I know it's unstable. Okay, it's much, much easier than having to compute the second variation. So let's see it in action. We in the same paper, we took an example of a rod in 2D that would be coiled, so it's a spring in 2D. So if I remove the mass, this thing would make a circle covered multiple times, one and a half, because of nu equal 1.5. And then I put a mass, and I will find different equilibrium. And here is one of them. This is the V that comes for this problem. Here is one of them. It crosses only one maximum, so J is 1, and bigger than 0, it's stable. I don't need to compute anything. And you have to understand that this is a very nonlinear sort. Theta of S is a very nonlinear sort of solution, and I get stability for free essentially. Now here are another ones. So this I know you know it's unstable because it looks very unstable, but I have a proof. So it starts at A. It has initial velocity because of the reference curvature. It shoots to B, then it falls back down, goes to C, and then ends at D. So that's a solution for my problem. It crossed a minimum once. That's the solution in phase plane. So we find that J is equal to -1, it's unstable. Here is another one that coils multiple times. It's the same parameters on all of my pictures. It crosses 3 maxima, 2 minima, so 3 minus 2 is 1, it's stable. For this same system with the same parameters, there are 2 more stable states and 5 more unstable, right? And you can classify them all and you can figure out stability automatically. So let's go back to my previous sort of problem. We looked at a birod, and we knew it was solution swinging in the potential V. So if you start with 0 velocity, the only thing is you can go down, and so you're always going to cross minima, and so all of those are unstable. Sorry, all of those are unstable. If you start with initial curvature, in my equations, that's correct, some of them will give you this starting with initial velocity. Then you're able to go across maxima, and then you can find some shapes which are stable, and I can prove that that and that is stable without any computation. Now this seems very theoretical, but there is a group in Bristol in 2012 that developed the following system. It's a ladder where B is stable, A and C are unstable. This is tied up. And the way it works is that if you unmount it, you get that the sides, flanges, would like to be curved in the reference state. Okay? They flatten them out, attach them to those middle spokes, which we will assume are rigid, and then they let go, and as a result, you get a shape that's like that. And of course, you have the opposite handedness as well. So what they wanted to do was have that sort of shape that's coiled up, and put it on a satellite, and once the satellite is up, you let it go, and you have a deployable boom. In their experiments, they made it short-ish, like you see here, but they wanted to be able to make it much longer. So what we did is that we wrote an energy for the system. Of course, it looks like our birod, so we can do this quickly. And this is the V profile. This is our straight state when theta equals 0. Theta is the angle between the tangent, I remind you. When theta equals 0, it's unstable because it's on a minimum. The helices are stable because they're on maxima. And then, of course, there is another solution which the engineers had never seen and didn't know about, which is you start close to one of the maxima and you swing down to the other. And that would look like that in the case of a long ladder. Now the engineers never saw it because it's unstable. And it's unstable because it only crosses a minimum. Okay? But the thing is that you can be sure that you will start inside the maxima only if theta primes is 0. So if there is any fabrication mistake on the reference curvature of those flanges, you could have a small theta prime. And as soon as you have a small theta prime, you can start a little bit on the left of that maximum and a little bit on, and finish a little bit on that right of that one. If I drew the ladder to the eye, it would look exactly like this, but now it's stable. So if you try to make a long ladder like that and you don't control your process very accurately, you could have a stable perversion. So this could be bad for the satellite thing, or maybe it could be good if you want to make a spring, because what you can see is that if you pull or twist on those helical equilibria, so here I'm only pulling, but because of the helical equilibrium, it's twisting as well. And here I'm only twisting, but because of the helical shape, it has to contract. If I do the same thing to a perverted solution, it behaves like this. So I have a twistless spring. So in a sense, that's fun to play with. And with Pedro Reis and Paul Grandgeorges, we are trying to build one of those right now at EPF. How much time have I got left? 10 minutes? Okay, very good. The next thing is to try to build effective properties for this. So I'm aware that I'm not the first one to try this, but to my knowledge, I'm the first one to try it like this. So the idea is I have a spring, and I could describe my spring as saying, okay, it's a Kirchhoff rod that's helical in its reference shape. But the problem is that when I do what is my shape now, I have a very nonlinear problem, and it's not so easy to solve. I can only do it numerically. What I would like to do, theoretically, is to say, okay, I would like to describe this rod as a straight rod that is completely extensible and that has bending stiffness properties which are very, very different from the sort of bending stiffness I feel if I'm trying to play on the string itself. So I would like to be able to do that sort of things, right? And you will see that we can. But to do that, we need a little bit of machinery. The first thing we can do is that these equations we had from the Kirchhoff equations, we can put in a Hamiltonian form. To do that, all we do is we take the energy density W, we do a Legendre transform, and we get an Hamiltonian. It is very important from the point of view of theory of rod that J is non-canonical. So it's not the usual 0, -110 sort of block. It's non-canonical, it implies N and M, and the shape of that J encodes that equation. It says we have a rod. So all rods, all Kirchhoff rods, must have the same J here. So and that's going to be important for us. Now, for a typical W, you remembered it was, for Kirchhoff rods, it was this quadratic form, half of the strains, K the strains. A similar Hamiltonian, the corresponding Hamiltonian is going to be half of the moment, the inverse of the stiffness matrix, the moment. And then the reference shape is encoded as a linear term in N and M in the Hamiltonian picture. Okay. So now let's take, before we do the coil, we're going to do the case of a twisted rod. And I'm only showing you a part of it. You have to do many length of the rod. If you're doing many terms, I told you the reference shape is included here. In fact, I have here in the V00 extensible. And the 1 over epsilon here says that the reference shape is highly twisted, because epsilon is going to go to 0 in my story. Okay? And I want to build an approximate Hamiltonian to this theory. But to do that, I want to develop in orders of epsilon, and I don't like that terms because it's large. One way to get rid of it is to choose my material sections to be all oriented the same way. And now I go away from choosing material framings which go with the principal directions. I have a price to pay. The Hamiltonian becomes a bit uglier. I still have a part that's diagonal, M1 square, M2 square, M3 square, but I have a part that's off diagonal. I have no terms that's very large. The price I pay is that I have terms that explicitly depend on S, factors that explicitly depend on S, and that change quickly with S. Okay? But all of the terms are now of order 1. And this is something that I can do for this thing as well. It's just a little bit more complicated. But in general, you can bring back any sort of coil to a Hamiltonian where all terms are of order 1 or smaller, and it depends on M, N, D, and R for external loads, and a quick explicit dependence on S. And then it's going to have this shape with the important J that is the right one for Kirchhoff theory. Now in comes a technique that was developed in the 60s, which is called the averaging methods, which is a technique people developed for celestial mechanics. where they had systems which are periodic and they want to predict the behavior of a very long time scales after many, many revolutions. So the story goes that if you took a different system of differential equations is a flow on some manifold. So let's look at only one line flow. Here it is. Now the story is that I would like to get to a simpler system than that one with the explicit dependence on S. Let's assume that I pick a vector field W, and then I take, and we're going to have to define W carefully in a second, but let's say I define one, and then I play the following game. For each point on the flow line of F, I follow the vector field W for a short time, say epsilon. Okay. Now I will get a new flow line, and if I picked W well, I get a new flow line that's simpler than the flow line I had for F. And that's basically the idea of the averaging method, in a nutshell. Now if I do that for one given W, but I apply it to all of the flow lines of F, so dashed goes to dashed, full goes to full, dotted goes to dotted, I define a new vector field G on the same manifold. Okay? And the idea of the averaging methods is that now I can solve for G, and that's simpler than solving for F. Once I've solved for G, I can follow W backward to get back to my solution of F. So this really works as an accurate approximation to the flow lines of F. Now, this is the picture story. When you do the computations, things get ugly quickly. To compute your field G, you have an expansion to Lie brackets, but you can do it. Now, people had tried to do that before for rods. You start with a flow field that's in the Hamiltonian form, and you want a flow field in the Hamiltonian form with a given J. Okay? And people have been working on the averaging methods for celestial mechanics ever since the 60s. It's still an active field of research. And the version of the theory has changed and changed and changed. And when people tried first this for rods, they gave up here because they thought J is non-canonical. I have nowhere that says how to choose a vector field W that will guarantee that G itself is also a Hamiltonian vector field with the right J. Okay? And there I thought I was very, very clever. I thought, aha, I just have to pick that W is itself Hamiltonian. And now I'm going to make an expansion into, I'm going to write my advection flow, which is the heart of this method, as a Hamiltonian field. And then I'm guaranteed, because of the play with Poisson brackets, that the resulting field G is going to be Hamiltonian with the same J. And I was like, I got this. And then I figured out that actually, this way of writing things, the very first paper by Horry in 68, that was how he did it. And then people started to change the way he wrote the theory and stuff, and nobody's doing it like this anymore now. But for this problem, that's exactly what we need to do. And there follows the methods where, order by order, you find your shape for omega, and once you have your shape for omega, you compute your effective field for G, and you do that order by order in an expansion in epsilon. And of course, we're not going to go through that detail. But for this ugly Hamiltonian we started with for the twisted rod, we get to a guiding center Hamiltonian that becomes isotropic. This coefficient and that one are the same. And you see that it became diagonal, and it's much simpler. And you see also that it's straight in its reference shape, right? So I get an effective theory for the twisted rod. Take-home message is this is really exactly what we want, because this function gives us the material parameters of the effective theory. So this tells us how the bending stiffness, that's in the guiding center frame. And this is the twisting stiffness. Now, this rod, so you have this one much longer, and I'm just going to draw it as a line because it takes too much, it takes unnecessary computer power to draw it like this. And I apply a force. Now you see that you see blue, red, and you know about those three lines, but essentially that has to do with the solving without using the method and the approximation. And you see that they're exactly on top of one another, so that's a good sign. And so you reproduce the bending problem of the twisted rod very well. But here it's not a good proof, so let's, instead of looking at the shape, I'm showing you the moment. So in black is the real shape, the real moments you will get along that shape if you solve for the original problem exactly. I mean, I did it numerically, but after well-converged numerics. In blue is it's the moments you get if you try to follow the blue vector field, the G's. And then in red is what I get if I follow W backward. Okay? Now I told you it's an asymptotic method. I can compute order by order, and you see that the same shown from a. You see there's a discrepancy after the wall, but it's there. can do the coil case. In black is what you get if you solve. So this is doing nothing to it, so it's not very interesting. I'll grant you that, right? But in black, it's what you get if you solve directly. The red is relation to black. That's what you apply. What happens if you apply a moment to it? You see it stays very good. Then I can apply a combination of those, and it stays good. Now you see there are some discrepancies, of course. I could push to higher than order 3, and I would get rid of that. There is nothing special with a helix. I can take any shape of coil and get an effective theory for it. And I've done a bunch. This is one example among many. There are many things we have to do in this research project. I think it's in a really good state to become a PhD thesis. It has to be compared with other effective column theories. I haven't had time to do it yet. The whole averaging method has been done for celestial mechanics, so it was done for initial value problems. And all of the theorem of convergence are done for initial value problems. I don't know of precise result for boundary value problems, so that there is a theory to be developed there to make sure it's going to work every time. I think the most exciting project is this one. Now, say you have a wire that's given to you, that is that diameter, and however long you like, and you want effective properties to be such. Now, how would you coil that rod to get those effective properties? So that would be the inverse problem for us. And I think it's doable, but there's some work to be done. Now, of course, all of the theorems come when the shape in the reference state is exactly periodic. Many real-life problems, like here, for example, towards the end, is no longer periodic, are not exactly periodic. So we need to generalize the theorem in the nearly periodic case. And of course, transforming Hamiltonian in general using flows is a rich idea, and I don't think it's been applied very much to the static of rods. And so I'm sure there is many more things to be found there. And for example, we could play with changing twist to rise. So if I pull this in an extreme way, I'm not going to do it because I will deform it completely, but eventually it's going to be straight and twisted instead of helical. Can we go that far with the perturbation theory or not? I'm not sure. That would be interesting to explore. And I'm left with thanking you. Avec plaisir.
Au départ, les formes qu'on avait dans l'état...
Bon, on va aller plus vite, hein.
L'état naturel et l'état courbé, ça ressemble à la distabilité.
Ah, merci. C'est pas un mètre ruban parce que il faut revenir 2 slides plus loin. Non, encore un slide plus loin. Voilà. Donc ici, en fait, les valves, elles sont attachées au réplum. Ce qui se passe, c'est que ces cellules-là sont en train de... Enfin, à un moment donné, elles reçoivent un signal de mort. Et donc ces cellules deviennent de plus en plus... Non seulement il y a de l'énergie qui est en train de s'accumuler dans la couche externe, mais en plus, cet attachement devient de plus en plus faible. Donc au départ, on avait essayé de faire le coup du mètre ruban, le truc des... Vous connaissez le système pour les gens qui font du vélo. C'est un ruban qui serait plié comme ça, quand il est droit, et il est content de rester dans cet état-là, mais c'est bistable. Il est aussi content, si vous l'aplatissez, il va s'enrouler dans l'autre direction. D'accord, vous pouvez faire ça pour attacher votre pantalon quand vous faites du vélo. Et donc la question de Sébastien, c'est est-ce que c'est ça qui est en train de se passer? La réponse c'est non. Si jamais on prend le système seul, il va s'aplatir automatiquement. Il n'est pas content de rester dans cet état-là. Et c'est essentiellement, c'est aussi parce que la couche d'en dessous, elle est contente de s'élargir. Donc il n'y a rien qui force le ruban à rester dans cet état-là. Ça avait été notre première hypothèse en fait, mais elle ne marche pas. Ouais. Ah, pardon, non, d'accord, ok. Donc, voilà mes 3 couches. Pardon, le slide d'avant, d'accord. Ok, donc 2 choses. Voilà mon système. Évidemment, les 3 couches, c'est une idéalisation. La couche active, c'est celle-ci qui voudrait bien se contracter dans la direction perpendiculaire au tableau. La couche passive, c'est celle-ci qui ne fait que nous donner de l'espace. Et puis j'ai une 3e couche qui est importante parce qu'elle est inextensible. D'accord? Donc ça c'est les ingrédients mécaniques. La question ensuite, c'est comment est-ce que cette couche-là veut se contracter? Et donc ce qu'on a fait, c'est que ce qui se passe dans la plante, c'est qu'elle augmente sa pression de Turger. Donc la pression à l'intérieur de chaque cellule de la couche active augmente. Et en résultat de ça, elle se contracte. C'est ça auquel on a eu beaucoup du mal. Enfin, c'est ça que les théoriciens ont eu du mal à accepter, moi y compris. On a commencé par dire à nos expérimentateurs, vous avez tort, c'est pas possible. Et en fait, c'est ça. Donc la pression augmente naturellement, et ça fait que la couche se contracte. Et donc, ouais. Et donc en fait, pour vérifier ça, ce qu'on a fait ensuite, c'est qu'on prend la couche, on dissèque la couche, et si jamais elle est attachée à rien du tout, elle est contente d'être contractée, donc elle a cette forme-là, ici. Et puis on la met en solution avec 1 molar de sel. Et donc là, ça change la pression osmotique. Et ça pompe l'eau à l'extérieur des cellules, et du coup, elle se relâche et elle prend sa forme plus longue. C'est là que la pression osmotique a joué. Mais c'était dans la manip de laboratoire et pas dans la plante. On n'a pas essayé de modéliser l'osmose, le transfert de matière de couche à couche. C'est ça, oui, complètement. Alors, de façon générale, le problème qu'on avait, c'était que pour l'expérience, si on commence à disséquer les couches, c'est difficile de savoir ce qui se passe à l'intérieur parce que ça a un énorme effet sur tout le système. Et donc l'expérience, elle peut facilement faire des mesures sur la couche externe et sur la couche interne, une fois qu'on a retiré la valve du réplum. Mais sur les couches, entre les deux, pour comprendre comment les choses sont en train de passer d'une couche à l'autre, on n'avait pas de façon de faire des expériences. Et du coup, on n'a pas essayé de modéliser cette partie-là du problème. Mais c'est clairement un problème intéressant et une partie intéressante de tout le projet. Oui, très probablement. Mais comment, le détail ouais. Je crois qu'il y a une question à l'arrière. Pardon? Oui, alors oui, et c'est parce que donc j'ai été vite là-dessus, mais pendant que un autre truc que Arabidopsis fait, c'est que Cardamine fait, pardon, c'est pendant la croissance, donc avant qu'on soit prêt à exploser, elle dépose des fibres de collagène dans la direction dans la largeur. Et ce que ces fibres de collagène font, c'est que donc il faut imaginer un ballon de baudruche sur lequel vous auriez mis du papier collant dans la direction azimutale, d'accord? Donc quand vous gonflez votre ballon, il ne peut pas s'étendre le long du papier collant, parce que ça c'est inextensible, et il va s'étendre en longueur. Et donc pendant la croissance de la plante, ces fibres garantissent que la plante grandit, que les cellules grandissent de façon allongée. Et puis le fait que ça se redirige, ça fait que ça se redirige. Maintenant, ça peut aussi grandir de façon latérale, et c'est pour ça que Cardamine a cette tête, a ces cellules qui sont plutôt carrées et plates. Dans le sens de la contraction. Alors le truc, le collagène, c'est que c'est dynamique si on regarde des échelles de temps qui sont sur la vie de la plante. Donc c'est construit et détruit en permanence. Et donc au départ, elles sont orientées comme ça pendant que la plante grandit. Les cellules sont en train de s'allonger. Et puis quand elle est prête, les cellules de collagène sont redéposées, mais dans la direction perpendiculaire. Et ça, c'est l'état où on n'est pas loin d'exploser. Les cellules de collagène sont verticales. Maintenant, si soudainement, aux échelles de temps de développement d'une plante, donc sur plusieurs heures, on augmente la pression de turgescence à l'intérieur de ces cellules, et bien maintenant, on a des fibres qui sont longitudinales. Et donc, quand j'augmente la pression, je ne peux pas aller dans cette direction-là. Donc, ce que je fais, c'est parce que j'ai une autre façon de le voir, c'est imaginez, en 2D, vous avez deux lignes droites, vous augmentez la pression entre les deux, mais vous dites que c'est inextensible. Pour augmenter le volume, vous allez faire ça. Et même si le bout de mes doigts se rapproche, ça augmente le volume entre mes deux mains. C'est ça qui se passe, mais une version 3D. Voilà. Exactement. Et c'est ça qui est fantastique. Ouais. On le laisse se détruire dans une direction, et puis il y a tout un phénomène pour déposer ces tracts de collagène, et ça réorienté. On n'a pas essayé de modéliser comment ça se réoriente. Ce serait aussi un chouette projet. Ce qu'on a fait dans le calcul numérique, c'est qu'on a mis un matériau fibré avec des angles donnés pour les fibres. Et comme estimation pour le module de Young des fibres, on a utilisé le module de Young qui correspond au collagène. Ouais, ouais.
Pas d'autres questions, on arrête là. Merci beaucoup.
Merci à vous.